Hi, and welcome to 16.3 Energy Levels and Atomic Spectra. In this lesson, we're going to be heavily using this table, which is located on page 3 of your reference table. And actually, there's two separate things going on here, right? So this is for a hydrogen atom and a mercury atom, and it's showing the energy levels of an electron in that hydrogen atom and mercury atom. So let's start with the hydrogen atom. We just have one proton in a hydrogen atom, and we have one electron, right? And this is just a model of what's actually happening. So what's actually happening is like the electron is in the shell. There's a probability of finding the electron at any point in that orbital. It's not like actually there in this one specific place. It's a probability of finding it there. But in this model, we'll just look at that. So there's the ground state here. This is n equals 1. And that's the lowest amount of energy that the electron could have. Well, if the electron gains energy, it jumps up to this next level, n equals 2. All right. And if the electron started in n equals 2, and then it dropped down here, then it lost energy. So this is a higher energy level, and the ground state is a lower energy level. And you could determine what the difference in the energy level is using these numbers over here. So it takes how much energy to go from n equals 1 to n equals 2. You'd have to do negative 13.6 minus negative 3.4. Did I do that right? Is it the initial minus the final? Let's see. Yeah, so for these, we're going to start with the initial minus the final. So if we were in the ground state, want to know how much energy does it take to jump up there? This is the initial photon energy, and this is the final. I drew over it, but it's negative 3.4. So you do initial minus final like that, okay? Negative 13.6 minus negative 3.4. That's what this is all about. And this becomes like plus positive. So yeah, cool. Anyway, so we're talking about an electron just gaining energy. Where does that energy come from? Does it within itself just creates the energy? No, we say that the electron gets that energy from an incoming photon. So here is our particle wave photon coming in, and it has, well, let's do the math from before, I guess. This is a whole thing. So the difference in the energy levels between n equals 1, the ground state, and n equals 2 is actually negative 10.2 electron volts. So this photon has 10.2 electron volts of energy that it's going to give to this electron in the ground state. So negative 13.6 plus 10.2 gives you the new electron energy of negative 3.4. This one now has negative 3.4 because it absorbed that photon. So they talk about absorbing the photon and then what happens when you emit the photon. So we answered the question where did this electron get the energy from to go to the higher energy level? It absorbed a photon. Well, let's think of it this way. Now we are starting in an excited state. Here's the electron. It has a lot of energy compared to this. It has more energy. And then it jumps down to a lower energy level, and the electron loses energy. Well, where does that energy go? Does it just disappear from the universe? No, what happens is a photon is emitted. So now the photon is leaving. So in the first situation, we absorbed a photon and went up. When we drop an energy level, a photon is emitted from the atom, and you could kind of see it glowing. This is kind of what happens with the aurora lights. You can think of that, where the oxygen atoms in the atmosphere and nitrogen atoms, they get into an excited state because they absorb the solar particles that get funneled into the poles, the magnetic poles, the north and south pole of the Earth. And so all those solar particles are being, concentrated in that area, and they're exciting the atoms of our atmosphere, except the atoms don't just hang out in that excited state, they drop back down. So they absorb the solar particles, and then when they drop back down, they emit photons, which looks like light. We're seeing the light that they're emitting because they were in an excited state and then they lost that energy. But it goes away. It doesn't lose. It's not lost from the universe. It's just transferred into photon. That's where the energy goes. So that's what it's all about. And then for the Mercury atom, it's the same situation, but they call the energy levels, A, B, C, D instead of N equals 1, 2, 3. So that's like this table in a nutshell. Let's use it to answer some questions. Number 1 says a photon is emitted as the electron in a hydrogen atom drops from the N equals 5 energy level directly to the N equals 3 energy level. What is the energy of the emitted photon? So they're looking for this. They are telling us information so that we could find EI and EF. The initial one was N equals 5. So let's look at hydrogen, N equals 5. What is the energy level there? So this table kind of is annoying. You really have to look, okay, N equals 5. See how close these lines are to each other? Make sure you're wearing your glasses. All right, so this is negative 0.54. And sometimes I'll check by going like, okay, if 3 is this, 4 is that, 5 is this. Yeah, negative 0.54. It's just hard to see because they're so close together. But that might be a common mistake. You might accidentally pick the wrong one because you looked across, right? So it's initially at this higher energy level and then it drops down to N equals 3, right? So we have negative 0.54 and N equals 3 is negative 1.51. And we use this equation, making sure that we do initial minus final. Substitute in, and the photon has an energy of 0.97 electron volts. Okay, it's being emitted, right? So we got a positive number for that. Number 2, an electron in a mercury atom, so it's going to be different from the hydrogen one, drops from energy level F to energy level C by emitting a photon. What is the energy of the emitted photon? So same deal. We're looking at F and C in a mercury atom. F is negative 2.68 and C is negative 5.52. Write your equation, substitute, and solve. You get 2.84 electron volts. That is the energy of the photon that is emitted. That's where the energy goes when you drop down from F to C. 3, which electron transition in the hydrogen atom results in the emission of a photon of greatest energy? N equals 2 to 1, 3 to 2, 4 to 2, or 5 to 3. Well, if we were being thorough, we could actually do the math, but if you look at the diagram, choice A says from 2 to 1, that's going to be a lot. We calculated that before. That was about 10 electron volts. Are any of the other choices going to be close to 10? Choice B was from 3 to 2. That difference is not close to 10. And you could see where this is going. 4 to 2. That's not close to 10. That's closer to 3. And then 5 to 3, that was the only one that might jump out at me because it's like a pretty big gap, but still not big enough to get to like 10 electron volts, which is the difference between these two. So choice A is the correct answer. And again, if you wanted to be thorough, definitely do the subtraction, but not necessary just to answer the question. It's more like, can you look at the diagram and see what's going on? Number 4, an electron in the C level of a mercury atom returns to the ground state. This one's, I like these types of questions. It says, which photon energy could not be emitted by the atom during this process? So remember, we're going from C to the ground state in a mercury atom. Let's take a look at what that looks like. So here we are at C. We have negative 5.52 electron volts, and we're going into the ground state, or A, all right? So remember, if we're going from a higher energy level to a lower one, what ends up happening is a photon gets emitted with the same amount of energy that you lose by jumping down. That's where the energy goes, right? The cool thing about electrons jumping around their shells is they don't exist in between the shells. They just jump straight to it. So you don't have to like take a pit stop at B and then go to C. You could just jump straight to, to A from C. So you could just jump straight to the ground state and skip energy level B altogether. That would give you like a big photon energy compared to the 2 photons that could be emitted if you go the other way. So the same initial and final conditions are going to be the same, but we'll get there differently. We're going to take a pit stop at B and see that little energy transition. There's going to be a very tiny amount of energy that gets released. And then we'll take another step because we're not there yet. We got to go down to the ground state, and that'll be like a medium-sized photon compared to this in terms of its energy. So here's like a more medium-sized one. So there's you could either have just one big photon being emitted, and I'm not talking size, but like in terms of its energy, or if you wanted to do the pit stop maneuver where you stop at B, you're going to have these two, right? So I see 3 different photons that you can get, and I see 4 answer choices in the question. So one of them is not going to be the correct answer. So what you got to do is do the math. You got to do the subtraction. So first let's do from C to A. That big jump straight to the ground state is going to give you a photon with 4.86 electron volts. And then if we did the pit stop maneuver, where we go to B first, so this is energy level B, which is negative 5.74. This photon has an energy of 0.22 electron volts, so this is this one over here that we drew. And then we're not there yet. Right now we're in B, and we got to get down to the ground state. So we're going from B to A, negative 5.74 minus negative 10.38. And this medium-sized, really it's not a different size, it's just a different amount of energy. This medium energy photon is 4.64 electron volts over here. So these are the 3 photons that could be emitted as you go from C to A. Which one is not there? Let's see. Okay, so here are our friends from before. This was from C to the ground level, and then we could take the pit stop from C to B, and then B to A. The one that's not there, choice D. Okay. Actually, looking at these answer choices, all you had to do was do this first one and be like, hey, the maximum amount of energy that I can emit going from C to the ground state is 4.86 electron volts. And although I understand that you could go from C to B and then B to A, and you'd have 2 smaller amounts of energy for each of those photons, which add up to the total energy here, you wouldn't get a energy that's greater than the amount that you get from C to the ground state. So that's an interesting point there. You could have just stopped after the first one and figured it out from there. But that's what's going on. Number 5, the spectrum of visible light emitted during transitions in excited hydrogen atoms is composed of blue, green, red, and violet lines. Which color of light in the visible hydrogen spectrum has photons of the shortest wavelength? Okay, so this one we can look back at that table that we learned about in Unit 15. We want to find the visible light with the shortest wavelength. You might know it already. We're talking about blue, green, red, and violet. Let's take a look at that. Okay, so we're talking blue, green, red, and then they throw in violet over here. Okay, so of those 4 answer choices, which has the shortest wavelength? And if you take a look, you could see on the left side is short wavelengths. On the right side, they get larger. So as you go this way, larger wavelengths. So as you go this way, same thing, larger wavelength. So that means that this must be the shortest wavelength. Don't forget, if you were thinking about frequency, these numbers here, 10 to the 14, that's all the frequency. So you could look at the frequency and be like, hey, this is a higher frequency, but it's moving at the same speed, which means that it must have a shorter wavelength. If it's a higher frequency, then the waves are like close together. They're higher frequency, shorter wavelength, and then they get spaced out. Okay? That's a horrible drawing, but you get the idea. We're talking violet. Number 6. A photon having an energy of 9.4 electron volts strikes a hydrogen atom in the ground state. Why is the photon not absorbed by the hydrogen? So, why wouldn't it be? Let's see. It's in the ground state. We're giving it 9.4 electron volts. Let's take a look at our table. So here we are in the ground state, and here comes a photon. Photon has an energy of 9.4 electron volts. Don't you want this energy to jump up to the very next energy level? Well, how much energy do you need to make that jump? Let's do the subtraction like we did before. If you remember, we got 10.2. It takes 10.2 electron volts. It's deficient in 10.2 electron volts in order to get to the n equals 2 level. So this photon better have 10.2 electron volts. Otherwise, it's not going to work. You can't exist in between. The electron's not going to be like, okay, you only gave me 9.4, let me hang out in this in-between level. No, it can only exist at the specific discrete energy levels. Cannot exist in between there. And since this is not enough energy, it's not going to cut it. We need 10.2. That's why it's not absorbed. So which of these answer choices closely is closely resembling what we just said? A says the atom's orbital electron is moving too fast. No. B, the photon is striking the atom. The photon striking the atom is moving too fast. No. C, the photon's energy is too small. Yeah, that sounds right. It's not 10 point whatever we said. It's only 9.4. All right, what was it? 10.2. The D, the photon is being repelled by electrostatic force. No. Okay, number 7. Which type of electromagnetic radiation is emitted when an electron in a hydrogen atom drops from the n equals 2 to n equals 1 energy level? So that's cool. We're going to find the photon energy, and then using that energy, we're going to determine the frequency, and then we'll look at that electromagnetic spectrum and match the frequency with the type of radiation. And let's see if that hint says that. It says first find the energy of the photon, then convert this to energy to joules, then find the frequency of the photon, then look in the reference table to see what type of electromagnetic radiation this is. So let's do that. N equals 2 to N equals 1. We just did that math, except we started here and went here. We want it to drop down, so technically this is EI. The given information, EI is negative 3.4 and EF is negative 13.6 electron volts. You write your equation, substitute, and as expected when you solve, this time you get positive 10.2 electron volts. That is the photon that gets emitted when the electron drops down. That's okay, cool. So now we know this energy of the photon, and we want to convert it into joules so that we can use this formula right here. We want to be able to use E equals HF because now we know E. We just calculated it. It's 10.2 electron volts. But this H, Planck's constant, which they give you on the front of the reference table here, is given to you in terms of joules. So we have an energy in terms of electron volts. We have to convert it to joules first using this conversion factor. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, so that we can use the E is equal to HF formula, because H, again, is in terms of joules. Why? So that we can find the frequency and use that frequency to determine what type of electromagnetic radiation it is, and that's what they're asking. So we're jumping literally all around the table the reference table for this question, which is a lot of fun. So let's carry out our plan of action. We're going to convert, write the number with the units, multiply by your conversion factor, making sure that your units are going to cancel out. Electron volts are in the numerator, so we want to put them in the denominator, and we're converting into joules. On the front of the reference table, we saw that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. You do that multiplication, and the energy in terms of joules is 1.632 times 10 to the negative 18 joules. I'll leave that decimal a little bit long for now because we're going to use it in the next part. Now that we know the energy in terms of joules, we can use the formula E is equal to HF. And we're going to solve for F. So F is equal to the energy divided by Planck's constant. The energy in terms of joules is 1.632 times 10 to the negative 18 joules divided by 6.63 times 10 to the negative 34 joule seconds. Okay, and then the frequency is going to be 2.46 times 10 to the 15 units for frequency. Joules cancel out. You get an inverse second, which is known as a hertz. So we're not done yet. We now know the frequency of that photon. Let's use the table to figure out where is 2.46 times 10 to the 15. Okay, 2.46 times 10 to the 15. That's going to be in this range here. Notice that the visible light is all 10 to the 14, so we're above violet. We are in the ultraviolet spectrum portion of the electromagnetic spectrum. Cool, so it's ultraviolet radiation. Ultraviolet. Actually, I shouldn't have even used like violet as the color because ultraviolet is not violet, it's ultraviolet. It's beyond what we can see with our human eyes. Cool. I love that question. We were bouncing all around that reference table. So good on you if you knew where to go. And if you weren't sure where to go, you missed a step somewhere, that's totally fine. All right. Because there's a lot involved with that. But hopefully you see now and you could do it in the future. Number 8. A hydrogen atom with an electron initially in the n equals 2 level is excited further until the electron is in the n equals 4 level. This energy level change occurs because the atom has, okay, so did it absorb or emit, and then is the photon 0.85 or 2.55? So we can tell right away, we can eliminate some choices. If we're going from n equals 2 to a higher energy level, we must be absorbing a photon. So it's going to be either A or C. So we're definitely not losing energy, we're absorbing energy. And then we need to calculate from 2 to 4. N equals 2 is negative 3.4, and 4 is going to be negative 0.85. So we need to do that subtraction. Actually, you could tell right away what the difference is going to be. It's not going to be 0.85. It's going to be closer to 2.55, but I'll show you anyway. So you get negative 2.55 electron volts. So that's going to be choice C. Okay, remember with the table, if you're jumping up, you're going to absorb a photon because you're gaining energy. And if you jump down, that's when you lose energy and you emit that energy in the form of a photon. So up is absorb, and if you jump down, you're emitting. Cool. And for number 9, it says a mercury atom in the ground state absorbs 20 electron volts of energy and is ionized by losing an electron. How much energy was required to bring the electron to the ionization state, and how much kinetic energy does the electron have after the ionization? So it says a hint how much energy was left over after the ionization. So we're talking about a mercury atom, and the electron is in the ground state right now. And it absorbs 20 electron volts of energy and becomes ionized. All right. Well, what that means is that electron gained so much energy that it is no longer bound to the atom, and the electron shoots off and it leaves the atom. And it shoots off with some velocity, with some kinetic energy. It's moving, right? So let's take a look at these numbers here. In the ground state, you need 10.38 electron volts to get to the ionization state. So this electron doesn't only gain 10.38 electron volts, there's 20 electron volts coming at it. So where does that remaining energy go? We had 20 electron volts. We used 10.38 of those electron volts to become ionized, which means we have 9.62 electron volts of energy remaining. Where does that energy go? It is transferred into kinetic energy of the electron. So it absorbs the 20 electron volts. Some of it is being used to become ionized, and the remaining is being used in the form of kinetic energy. That electron starts moving away from the atom. So how can we represent those ideas for here? For part A, we can still do the same process where initially in that ground state and then in that ionization state, you have 0 joules or 0 joules, 0 electron volts of energy there. So that's like initial final. So here we say that there was 10.38 electron volts of energy taken from that photon that it absorbed. So part B says, how much kinetic energy does this electron have after the ionization? You're just going to take the total energy that you were given, subtract the energy that we used in part A to become ionized, and the remaining energy, 9.62 electron volts, is equal to the kinetic energy of that electron as it becomes ionized and moves. It's moving, so it has kinetic energy as it moves away from the mercury atom. Cool. Okay, number 10 is pretty self-explanatory, so I'll let you read that on your own and answer it on your own. Number 11 says the diagram below represents the bright line spectra of 4 elements A, B, C, and D. That's these 4 over here. And the spectrum of an unknown gaseous sample. Okay. Based on the comparisons of these spectra, which 2 elements are found in the unknown sample? So we want to, like, this sample is emitting photons of certain frequencies, and we know which frequencies are emitted by these elements. So we want to compare them, and if the frequencies match up, then we know that that is in that sample. So let's go from left to right here. So for this line here, I see a line here in element B. So I guess I could draw it like this. This one is good with that. So it's green, green. All right. And then this second line here, it looks very close to it. All right. Where is that? That's going to be all the way. Where does it match up? Oh, right here. Okay. So let's make there. And then so far, this one's looking good. So right away, we can tell that B and C are looking good. Let's see if the rest of them match up. So here, nothing yet, nothing. Oh, okay. So here, this third line in the unknown sample matches up with the second line in sample C. And then, okay, let's see. This is looking kind of good, but it's a little bit further away. Okay, this matches up perfectly with element C. So far, so good. We have match for all of these lines so far. They're all accounted for. So here we go. Boom. Is this anywhere? Oh, it's not in C, but guess what? It's in B, so that's good. We're confirming that element B is in the unknown sample because that matches and the first line matched. And then this last line, where is this going to go? Not element B, but it matches with element C. It does match with element D too, but none of the other lines in element D match up. So we're not going to include that one. See, like this would be, here's element D. I don't see a line over there for element D. I don't see a line over here. I don't see a line over here. See how that works? You're just comparing the thing. And technically, this one's no good either. It's a slightly different frequency. You see that? No good, no good, no good, no good. So definitely not A and D. And it's definitely going to be B and C. So let's get a nice circle over here. B, and C. Choice C. Awesome. All right. Hopefully you enjoyed this. Thanks for watching. Anyway, that's about it. Thanks for watching and have a great day.